So from last time, we had a problem that we were left with, specifically 5 times the log base 4 of x plus 2 is equal to 17. And using the techniques we talked about in the first part, you should have been able to work through this one fairly easily to get a solution of x equals 64, which when you double check does work out for that particular equation. So if you didn't get that answer, go back and double check the first video and see if you can see where you got stuck. Okay, so we're going to continue with the idea of going through examples, and with each example we're going to do over the next few videos, we're trying to pick up new strategies, techniques, and looking for ways to recognize how we could approach a particular logarithmic equation if we were faced with one. So in the next one that I want to look at, we've got to solve for x in the case of 7 times the log of x squared minus 3x plus 3 is equal to 10. Now, even though we're not asked for it, it's probably a good idea to go ahead before we start manipulating this equation and take note of our restrictions. So in this case, our argument is x squared minus 3x. That's what's inside of the logarithm, and this needs to be greater than 0. We're just going to kind of hold on to that piece of information for a little bit and then come back to it at the end. So using the general method that we talked about in the first video, we're going to go through our steps here. So one thing we may notice if we wanted to try and categorize this is we should look at this and say I've got logs and constants. And that's going to tip us off as to how we're going to need to solve this for x in the end. So again, we'll just kind of keep that in mind as we move on. So step 1, we're told to isolate the log. So we want to isolate the log. And since we've got logs and constants, this is going to mean let's get the constants onto one side and the log on the other. So we could start by subtracting 3 from both sides, and that would put us at 7 times the log of x squared minus 3x is equal to 7. And then it's not isolated until we've removed any coefficients. So in this case, we're going to go ahead and we're going to divide both sides by 7. And if we do this, we're going to end up with the log of x squared minus 3x is equal to 1. So this is what we're going to use to help solve. So step 2 is, since we've got a log and a constant, we're going to try to rewrite this as an exponential expression. So we will rewrite this equation. And in doing so, if we have the log of x squared minus 3x equals 1, we know that to translate this into an exponential equation, this tells us that x squared minus 3x is going to have to be equal to our base, which is 10 raised to the power of 1 in this case. So, and we could, to the power of 1, essentially we can just kind of get rid of that. And we've got 10. So this is the equation that we're going to want to solve. So now that's all we need to do is just go ahead and solve this for x. So if we solve for x, what we've got is we've got a quadratic. So let's go ahead and set it equal to 0. So we've got x squared minus 3x minus 10 is equal to 0. This will factor as x minus 5 times x plus 2. And since the product of these two factors is equal to 0, we can break this up and set each of the factors equal to 0 individually. And if we do this, we see that we've got 2 possible solutions. X could be equal to 5, or x could be equal to -2. Now, before we pat ourselves on the back and run off, we really need to check these in order to make sure that we're not going against any possible restrictions that we may have. Now, depending on the complexity of our argument, it's maybe an easier we might have an easier time, rather than trying to solve that original restriction for x, just plugging these into our function to see if we have any issues. So let's see. We want to check that whatever our x is, if we square it and subtract 3 times it, it's going to be greater than 0. So we're going to check our two solutions in this restriction. So if we tried x equals 5, what we would end up with is we'd have 5 squared minus 3 times 5. This would give us, what, 25 minus 15. So is this greater than 0? Yes. So this is a solution that we can check off. And then we're also going to want to go ahead and check x equals negative 2. So we'd take negative 2, we'd square it, which would give us 4, and we'd subtract 3 times negative 2, which would just be like adding 6. So this is also going to give us a positive number. So it turns out that both of these are actually solutions. So we can go ahead and conclude that x is equal to 5 and minus 2 as an answer to this one. So we solved it and then we checked it. Very important steps. Okay, so let's go ahead and try the next one that I wanted to work through. Okay, so this is a little off. So let me just move this really quickly. All right, so we are looking at this one next. So we're going to solve this for x. We've got 3 times the ln of x minus 2 is equal to 1 minus the ln of x. So again, I'm going to make 2 quick notes before I move on. The first one is restrictions on the domain. So I'm going to look at both of these. I'm going to say because of this and because of this, our argument is x. So whatever solutions we may have, they're going to have to be strictly greater than 0. The other thing that I'm going to make a note of here is that I've got logs and constants. And because of this, I'm going to get the logs on one side and the constants on the other. This is just going to make this an easier process for us. Now in this case, we've got 2 logs, the ln of x, 3 times the ln of x and minus ln of x. Since we've got the ln of x in both cases, the argument is the same. We're actually going to be able to combine these as if we were just adding or subtracting any variable, like in any x term or y term. So I'm going to go ahead and I'm going to add the ln of x to both sides. And I'm also going to add 2 to both sides. And if I do this, I've got 3 ln of x's plus 1 ln of x, so that's going to give me 4 times the ln of x. And on the other side, I've got 1 plus 2, which is 3. Now we've got almost an isolated logarithmic term, so we really need to isolate this further. So we're going to isolate the log. And for us, this means that we're going to have to divide both sides by 4. And when we do this, we get the ln of x is equal to 3/4. So here we go again. We've got a log on one side isolated and we have a constant on the other. So we're going to go ahead and we're going to use that first property of logs to redefine this and rewrite this as an exponential. So we're going to go ahead and we're going to rewrite. Now, one thing to keep in mind here is that the ln of x is the log base e of x. So that's our base. It's going to be important as we put this together, because in rewriting this as an exponential, we're going to have x is equal to our base, which is e, raised to the power of 3/4. And that's actually our answer. So that's our solution. And we could get an approximation of this if we were so inclined or asked. This is about 2.117. And again, we really need to check this before we move on. And again, we check it with the restriction that x has to be greater than 0. Well, this is clearly a positive number, so we can check this off. So our solution here is x is equal to e to the power of 3/4. And that's our answer. Okay, so two more examples of how we can go through these types of logarithmic equations. So for the next before the next video, I would like you guys to try, sorry about that, I'd like to try this one. So not too bad, but solve this for x. You got the ln of x squared minus 99 is equal to 0. So go ahead and try solving for x, checking, make sure you check your restrictions that you may have on this, and see how it goes, and we'll talk about the answer in the next video.